Welcome back, everyone, to another deep dive. This time, we're going to be exploring the world of Japanese engineering.
Ooh, exciting.
Yeah, you've given us quite a collection of documents here.
Yeah,
It looks like they're straight out of a mechanical engineer's toolbox.
absolutely.
Tables, diagrams, technical terms, and it's all in Japanese. So
All in Japanese.
we're on a mission to decode these for you and discover what secrets they might hold about engineering practices and design principles in Japan.
Gonna be like a technical Rosetta Stone, I think.
Yeah, we have quite a stack here.
Yeah, we do.
I'm just looking at some of the titles here. 02sushu.pdf and 02a sushu2wuya.
Right.
So I'm guessing table of contents and unit conversions.
You got it.
All
Those
right,
are pretty standard for any engineering handbook.
Yeah.
But then we've got things like 032.pdf, 12a, 220, teltitudefitil.pdf.
Wow.
So we're looking at materials dimensions,
Okay.
joining, which is probably welding, I would say.
Right.
And even heat transfer. So it's a pretty wide range here from basic components to some more theoretical concepts.
So what jumps out at you as we start digging into the content here?
Honestly, the first thing I noticed was just the sheer amount of detail
Really?
on even like the simplest things.
Okay.
For example, there are pages and pages of tables detailing the dimensions and weights of all these different types of steel pipes.
So like, why so many different types of pipes?
Well, think about the variety of applications.
Yeah.
I mean, you wouldn't use the same pipe for a water supply system as you would for transporting chlorine gas, right?
Right.
So we see tables for everything from STK, which is your general structural carbon steel,
Okay.
to STPY, which is specifically for chlorine gas.
Oh.
There's even STKR for square-shaped steel pipes.
Oh, wow.
It's a lot.
So it's all about picking the right material for the specific job.
Exactly.
But with so many options, how do engineers make sure everything is consistent and compatible?
That's where those Japanese industrial standards come in, or JIS as they're often called. And you'll see those referenced constantly throughout these documents.
Okay.
And they basically ensure that materials and components meet very specific quality and performance benchmarks,
Oh.
no matter who manufactured them.
So it's not enough to just have a steel pipe. It has to be a steel pipe that meets this specific JIS standard.
Right.
What happens if an engineer just decides to ignore these standards?
Well, it could be disastrous.
Right.
I mean, imagine a pipe failing because it couldn't handle the pressure or the temperature requirements.
Right.
These standards are there to ensure safety and reliability.
Right.
And that's a recurring theme that I'm noticing in these documents, is this real emphasis on precision and doing things right.
That's interesting.
Yeah, it's not just about building something that works, it's about building something that works flawlessly.
That's fascinating.
And that attention to detail goes beyond just the materials.
Mhm.
We also see it in the way they approach calculations and formulas. For instance, there are detailed formulas for determining things like the pressure capacity of cylinders, the fatigue strength of welded joints, and even the power transmission capabilities of gears.
Hold on, let's back up for a second.
Sure.
Could you explain what fatigue strength means?
Of course, fatigue strength is basically how much stress a material can handle over repeated use.
Okay.
So think of a bridge
Okay.
with cars driving over it every single day.
Yeah.
That constant stress can eventually cause tiny cracks to form, and if that material's fatigue strength isn't high enough,
Right.
those cracks can grow and lead to failure.
So these engineers are factoring in the long-term use of these designs.
Absolutely.
What happens if they miscalculate something like that?
Well, it could compromise the entire structure or system.
Wow.
That's why these calculations are so critical,
Yeah.
especially in a country like Japan that's prone to earthquakes.
It's like every calculation, every material choice carries a huge weight of responsibility.
It does. It's a bit intimidating.
Yeah, it is.
But it also shows this deep commitment to quality and safety.
Yeah.
And that's not just evident in the calculations, but also in the way they document everything
Okay.
with such meticulous detail.
So what are some of the more intriguing details you've come across?
Well, some are more obvious than others.
Right.
Like we already mentioned those JIS standards
Yeah.
called out for everything from H-beams to plane bearings.
Right.
But then there are things that are just well unexpected.
Like what?
For example, there are detailed specifications for wire mesh panels shaped like diamonds.
Okay.
And get this, tortoise shells.
Tortoise shell.
Tortoise shells.
What on earth would you use that for?
That's a great question. And to be honest, I haven't figured that one out yet.
Really?
It's these little mysteries that make this deep dive so captivating.
Hmm.
It reminds me of those documentaries where archaeologists find a tiny artifact and suddenly a whole lost civilization comes into focus.
I know what you mean.
Uh,
Like a little puzzle piece that hints at a much bigger picture.
Exactly.
So what other unexpected details have you uncovered?
Well, in one of the appendices, I found an international atomic weight table.
An atomic weight table. That seems a bit out of place in a mechanical engineering handbook.
You'd think so, wouldn't you?
Yeah.
But it just highlights how interconnected different fields of science can be.
Right.
Understanding atomic weight could be essential for material science and developing new alloys.
So even though these documents are hyper-focused on engineering,
Yeah,
they also acknowledge the broader scientific context.
absolutely.
That's pretty cool.
It is, and it makes you wonder what other unexpected connections we might find as we keep digging.
Speaking of digging, we were talking about that meticulous approach to calculations and formulas earlier.
Right.
Is there a particular formula that stands out to you?
Well, there are so many to choose from, but the one for calculating the pressure in a thin-walled cylinder is a good example.
Yeah.
It states that the pressure is equal to twice the product of the tensile strength and the wall thickness divided by the diameter of the cylinder.
Okay, that sounds straightforward enough.
Yeah.
But what are the real-world consequences if an engineer gets that calculation wrong?
Well, the cylinder could rupture,
Oh, wow.
leading to anything from a minor leak to a catastrophic explosion.
That's a sobering thought.
It is. It underscores the importance of getting those calculations right, especially when you're dealing with pressurized systems.
Right.
It's not just about theoretical numbers, it's about real-world safety and reliability.
This is what I find so fascinating about engineering.
Yeah.
It's where theory meets reality, and the stakes can be incredibly high.
Absolutely.
We've talked a lot about steel, but I'm curious about other materials mentioned in these documents.
Sure.
What else have you found?
Well, we've already touched on copper tubes, including that historical reference to steam locomotive boilers.
Right.
But there's also a lot of information on bearing alloys,
Okay.
which are the materials used in those smooth surfaces that reduce friction between moving parts.
Like the bearings in a car engine or a rotating shack?
Exactly.
Okay.
And those bearings need to have very specific properties,
Okay.
like low friction, high resistance to wear, and the ability to withstand high temperatures.
So it's not just any old metal that can be used for bearings?
No, not at all.
Okay.
And the documents provide tables detailing the composition of these alloys and their key performance characteristics.
So we've got steel pipes, copper tubes, bearing alloys.
Right.
What else?
Well, there's even a whole section on heat transfer,
Oh.
which might seem a bit outside the scope of mechanical engineering at first glance.
What could mechanical engineers possibly need to know about heat transfer?
It's actually crucial for designing systems that involve heat management.
Oh, okay.
Think of engines, power plants, even the heating and cooling systems in buildings.
Right.
The documents include diagrams and formulas for calculating heat transfer through conduction, convection, and radiation.
Okay. I vaguely remember those terms from high school physics, but I couldn't explain them now.
Well, think of conduction as heat moving through direct contact,
Okay.
like when you touch a hot stove. Convection is heat transfer through a fluid, like air or water.
Okay.
And radiation is heat transfer through electromagnetic waves, like the heat you feel from the sun.
Okay, that makes sense.
Yeah.
So why would an engineer need to calculate all of those?
Well, let's say you're designing a heat exchanger,
Okay.
which is a device that transfers heat from one fluid to another.
Right.
You'd need to consider all three modes of heat transfer to optimize its efficiency.
Right.
The documents even include information on insulation materials and recommended thicknesses for different applications.
It's incredible how these handbooks seem to cover every possible scenario an engineer might encounter.
It's all about being prepared and having the tools to solve a wide range of problems.
Right.
But speaking of problem solving, there's one more element that really stands out in these documents,
Okay.
and that's the emphasis on standardization.
We talked about the JIS standards earlier, but you're saying it goes beyond just materials.
Absolutely.
Okay.
There are standard dimensions for bolts, nuts, and other fasteners, standard sizes for pipes and fittings, even standard symbols and notations used in engineering drawings.
So it's like there's a standardized blueprint for pretty much everything.
Pretty much.
Yeah.
Why is that so important?
Yeah. Why is that so important?
Well, standardization brings several benefits.
Okay.
First, it ensures interchangeability.
Okay.
So if a part breaks, you can easily replace it with another part that meets the same standard, no
Right.
matter who made it.
That makes sense.
Second, it streamlines the design and manufacturing processes.
Okay.
Engineers don't have to reinvent the wheel every time.
Right.
And third, it promotes quality control. By adhering to strict standards, manufacturers can ensure consistency and reliability across their products.
It sounds like standardization is a key factor in that reputation for precision and quality that we associate with Japanese engineering.
It definitely plays a role. And it's something that we see reflected throughout these documents, from the specific materials used to the way those materials are tested and documented.
You know, for someone who's not an engineer, I'm finding all of this surprisingly fascinating.
It is fascinating stuff.
I'm particularly intrigued by the section on shaft couplings.
Okay.
Can you tell me about those?
Shaft couplings are devices used to connect shafts together,
Okay.
and they're essential for transmitting power in rotating machinery.
Right.
The documents detail various types of couplings, including rigid, flexible, and fluid couplings.
Okay. Those terms sound familiar, but I need a refresher.
Sure.
What's the difference between them?
Well, a rigid coupling provides a fixed connection between two shafts,
Okay.
so it ensures perfect alignment.
Okay.
They're often used when precise positioning is critical,
Right.
but they're not very forgiving if there's any misalignment or vibration.
So if the shafts aren't perfectly aligned, a rigid coupling could cause problems.
Exactly. That's where flexible couplings come in.
Okay.
They allow for some degree of misalignment. And they can absorb vibrations, making them more suitable for applications where there's likely to be some movement or flexibility required.
It makes sense. So what about fluid couplings? What are they used for?
Fluid couplings use a fluid, typically oil, to transmit torque between shafts. They're great for smooth starts and stops, like in heavy machinery, and they can protect the drive system from shock loads.
So they're like a built-in shock absorber for rotating systems.
Exactly.
That's clever.
It is, and it highlights the level of ingenuity that goes into even seemingly mundane components.
Speaking of ingenuity, what about gears?
Ooh, gears.
Those always seem so complex to me.
Gears are fascinating.
Yeah.
They're essentially toothed wheels that transmit power and motion from one shaft to another.
Right.
And the documents provide a wealth of information on gear design calculations and selection. They cover everything from basic spur gears to more specialized types like helical gears, bevel gears, and even worm gears.
Worm gears, those sound intimidating. What are they used for?
Worm gears are unique because they can achieve very high gear ratios,
Okay.
meaning they can significantly reduce speed and increase torque.
Yeah.
They're often used in applications where you need a lot of power in a compact space,
Okay.
like in winches or steering mechanisms.
So they're all about trading speed for power.
Exactly.
Interesting. And what about those other gear types?
Well, spur gears are the most common type.
Okay.
They're simple, efficient, and relatively inexpensive.
Okay.
Helical gears are similar, but their teeth are cut at an angle,
Okay.
which makes them quieter and smoother in operation.
Hmm.
And bevel gears are designed to transmit power between shafts that intercept at an angle.
It sounds like there's a specific gear for pretty much every application.
There is. And these handbooks provide all the information an engineer needs to select the right gear for the job,
Right.
taking into account factors like speed, torque efficiency, and noise level.
It's amazing how much thought and precision goes into every aspect of engineering,
It is.
even something as seemingly simple as a gear.
Absolutely. It's all about understanding the fundamental principles and applying them in a way that meets the specific needs of the application.
You know, throughout this discussion, the concept of torque keeps coming up.
Yeah.
It seems particularly relevant when we talk about gears and couplings.
Yes.
Can you explain what torque is and why it's so important in engineering?
Sure. Torque, in simple terms, is a twisting force that tends to cause rotation.
Okay.
Think about using a wrench to tighten a bolt.
Okay.
You're applying torque to the bolt.
Right.
In engineering, torque is essential for understanding how power is transmitted and how rotating components interact.
So when we're talking about gears and couplings,
Yes.
torque is a measure of how much twisting force they can handle.
Precisely. Gears are designed to transmit torque from one shaft to another,
Right.
and couplings need to be able to withstand that torque without failing.
It sounds like understanding torque is crucial for ensuring that everything works smoothly and reliably.
It is. And these documents provide the tools and information needed to calculate torque accurately and select the appropriate components for a given application.
It's like we've been given a glimpse into the inner workings of Japanese engineering.
We have. And it's been a fascinating journey so far.
It feels like we've only just scratched the surface of these documents.
I know, right?
We've gone from steel pipes to atomic weight tables to tortoise shell-shaped wire mesh.
It's amazing how much is packed in here.
It makes you realize just how much goes into engineering.
Yeah,
It's not just about knowing formulas and materials.
right.
It's about understanding how all those pieces fit together to create something functional and reliable and safe.
Yeah, it's a systems approach for sure.
Yeah.
And it's really evident in the way that these Japanese engineers approach their work.
Yeah.
There's a sense of thoroughness, a meticulous attention to detail that
Right.
really permeates every aspect of these documents.
So for our listener who maybe isn't an engineer,
Yeah.
what's the big takeaway here?
Yeah.
What can they learn from this glimpse into the world of Japanese engineering?
I think the biggest takeaway is that these documents reveal a culture that prioritizes precision,
Mm.
standardization,
Right.
and a relentless pursuit of quality.
Yeah.
And those values are reflected not only in the products that Japan produces, but also in its infrastructure, its manufacturing processes, even its approach to problem solving.
It's about striving for excellence in everything you do, no matter how small or seemingly insignificant.
Absolutely. And that's a lesson that can be applied in any field.
Yeah.
Whether you're designing a skyscraper, writing a piece of code, or even just organizing your kitchen pantry.
That attention to detail, that commitment to getting it right,
Right.
it can make all the difference.
Absolutely.
So as we wrap up this deep dive,
Yeah.
what's one final thought-provoking idea you'd like to leave our listener with?
The most thought-provoking thing for me has been the sheer volume of information contained within these handbooks.
Yeah.
We've only explored a tiny fraction of it.
I know.
But imagine the vast repository of knowledge and expertise that they represent.
It's like we've opened a door to a hidden library,
Yes,
and we've only had time to glance at a few books on the first shelf.
precisely.
And it makes you wonder what other treasures are waiting to be discovered within those pages.
Right. What insights and innovations might emerge from delving deeper into that world?
Yeah, that's a good point.
Hmm.
It's a reminder that there's always more to learn,
Right.
always new connections to be made,
Yeah,
always deeper levels of understanding to be achieved.
absolutely.
Well said. Well, on that note, I want to thank our listener for joining us on this journey into the intricate world of Japanese engineering.
It's been a pleasure.
We hope you've gained a new appreciation for the dedication, the precision, and the ingenuity that go into building the things we rely on every day. Until next time, keep exploring, keep asking questions, and keep that thirst for knowledge alive. We've covered so much ground in this deep dive,
We have, haven't we?
from steel pipes to atomic weight tables to tortoise-shell-shaped wire mesh.
It's incredible to think that we've only just scratched the surface of these documents.
I know, and yet it feels like we've already learned so much about Japanese engineering.
Yeah.
I think what strikes me the most is the sheer depth of knowledge and the meticulous attention to detail that's evident in every page.
Absolutely. It's like they've anticipated every possible scenario and provided the tools and information needed to address it.
And that commitment to precision and standardization, it really seems to be at the heart of their engineering philosophy.
It does, doesn't it? It's not just about building something that works. It's about building something that works flawlessly and reliably every single time.
So for our listener who maybe isn't an engineer, what's the key takeaway here? What can they glean from this glimpse into the world of Japanese engineering?
You know, I think the biggest takeaway is that these documents reveal a culture that values excellence above all else. It's a culture that prizes precision standardization and a relentless pursuit of quality.
And that's reflected not only in the products that Japan produces, but also in its infrastructure, its manufacturing processes, even its approach to problem solving.
It's everywhere you look.
It's about striving for perfection in everything you do, no matter how small or seemingly insignificant.
Right. It's about sweating the small stuff because they know that the small stuff matters.
It's like that old saying, a chain is only as strong as its weakest link.
Exactly.
And they've taken that to heart in their engineering practices.
Absolutely.
So as we wrap up this deep dive, what's one final thought-provoking idea you'd like to leave our listener with?
The thing that keeps coming back to me is this sense of wonder.
Wonder.
Yeah, wonder at the sheer scope of human ingenuity. We've only explored a tiny fraction of these documents,
Right.
but they represent centuries of accumulated knowledge and experience.
It's humbling, isn't it?
It is. It makes you realize that there's always more to learn, always new discoveries to be made, always new connections to be forged.
And it's that spirit of exploration, that insatiable curiosity, that really drives innovation and progress.
Absolutely. It's what pushes us forward as a species.
Well said. Well, on that note, I want to thank our listeners for joining us on this journey into the fascinating world of Japanese engineering.
It's been a pleasure.
We hope you've gained a new appreciation for the dedication, the precision, and the ingenuity that go into building the world around us.
And who knows? Maybe this deep dive will inspire some of you to explore the world of engineering yourselves.
That would be fantastic. Remember, folks, keep exploring, keep asking questions, and keep that thirst for knowledge alive. Until next time.